So, here's something worth thinking about as you settle in tonight. Some of the light reaching your eyes has been traveling for billions of years, and along the way, the empty space it was crossing slowly stretched and stretched until the light itself arrived a little redder than it began. That reddening is the whole story in miniature. It is the fingerprint of a universe that will not sit still, one that has been quietly growing for as long as it has existed, and that nobody fully understands, even now. Tonight, we are going to sit with all of it, gently, the parts that make clean sense, and the parts that still confuse the people who study them for a living. You don't need to follow every step. You don't need to hold anything in your head. If you drift off somewhere along the way, that is perfectly fine. The ideas will still be here in the morning, and so will the universe. So let's start where the story actually starts, not with a telescope and not with an equation. Let's start on a dark night with a very old and very simple question. Why is the sky black? It sounds like a question with an obvious answer. The sky is dark because the sun has gone down, and the stars are far away, and space is mostly empty. That feels like enough. For most of human history, it was enough. But a few careful people looked up at that darkness and realized it did not add up. And the reason it did not add up turns out to be one of the first quiet clues that the universe is not what it appears to be. Here is the trouble. Imagine, for a moment, that the universe is infinitely old and infinitely large, and that it is filled fairly evenly with stars going on forever in every direction. That was the reasonable picture for a long time. A cosmos with no beginning and no edge, calm and eternal. It is a restful idea, honestly. But if it were true, something strange would follow. In an infinite forest, no matter which way you look, your line of sight eventually lands on a tree. Look far enough in any direction and you hit bark. Now do the same with stars. In an infinite universe full of them, every single line you could trace out from your eye, in any direction at all, would eventually end on the glowing surface of a star. And if every direction ends on a star, then the whole sky, every patch of it, should be as bright as the surface of the sun, not just the little dots, the black gaps between them too. The entire night sky should be a wall of blinding light. But it isn't. You can walk outside tonight and see for yourself. The sky is mostly dark, with scattered points of light on a deep black background. So one of the assumptions has to be wrong. The universe cannot be, all at once, infinitely old, infinitely large, evenly filled with stars, and unchanging. Something in that comfortable picture has to give. This puzzle has a name. It is usually called Olbers' paradox, after Heinrich Olbers, a German doctor and astronomer who wrote about it in the 1820s, which is a little unfair because he was nowhere near the first to notice it. Johannes Kepler had worried at it 2 centuries earlier. Others circled it in between. But the name stuck to Olbers, and names in astronomy have a way of sticking to whoever happened to be standing nearby, rather than whoever got there first. You will see that pattern again tonight, more than once. For a long time, nobody had a good answer. People suggested that maybe dust in space was soaking up the faraway starlight and hiding it. It was a reasonable guess. But it doesn't work, and the reason it doesn't work is quietly beautiful. If dust sat out there absorbing starlight for long enough, it would heat up. And anything that heats up eventually glows. The dust would end up shining just as brightly as the stars it was meant to be hiding. You cannot cheat your way out of the problem with a curtain, because in an eternal universe the curtain becomes a lamp, So the darkness is real, and it needs a real explanation. And the explanation, when it finally came, was not about dust at all. It was about time and about motion. The night sky is dark for two reasons, and both of them are clues we will spend the rest of tonight unfolding. The first reason is that the universe is not infinitely old. It had a beginning, a little under 14 billion years ago. And because light travels at a fixed speed, it can only have traveled so far in that time. When you look out into space, you are looking backward into the past, and there is a limit to how far back you can see. Beyond a certain distance, the light of the most distant stars simply has not had time to reach you yet. The forest is real, but it has an edge in time, and past that edge, the trees have not shown up in your eye yet. So most of your lines of sight run out into darkness before they ever land on a star. The second reason is the one this whole night is about. Space is expanding. The most distant light is not only faint from crossing a vast distance, it has been stretched by the growing of space itself, its energy drained away, its color pulled down out of the visible and into the invisible. Some of the oldest light in the universe is still arriving right now from every direction, but it has been stretched so far that your eyes cannot register it at all. It is there. You are bathed in it. It is just no longer light you can see. So the dark sky is not empty, and it is not simple. It is a message. It is telling you that the universe had a birthday, and that it has been growing ever since. Edgar Allan Poe, of all people, guessed at part of this in 1848, in a strange prose poem about the cosmos. He reasoned that the darkness itself meant the faraway light had not yet arrived. He had no telescope evidence, only the force of the argument. And he was, more or less, right. A poet felt the shape of the answer decades before the astronomers could prove it. But we are getting ahead of ourselves. To understand how anyone could possibly know the universe is growing, you first have to solve a much older and much more frustrating problem. Before you can measure how the universe moves, you have to measure how far away things are. And distance, in astronomy, is the hardest thing in the world to pin down. So let's come back down, closer to home, and start with the oldest question of all. How do you measure the distance to something you can never reach? Start with a trick your own eyes do without asking. Hold a thumb up at arm's length, close one eye, then close the other and open the first. Your thumb jumps against the background. It hasn't moved. Your two eyes just see it from slightly different angles, and that small shift, that jump, is enough for your brain to judge how far away your thumb is. Bring it closer, and the jump gets bigger. Push it further away, and the jump shrinks. Distance and jump are tied together, and if you know one, you can work out the other. Astronomers use exactly this trick, only their two eyes are the same telescope, 6 months apart. In the summer, the Earth sits on one side of the sun. In the winter, it is all the way around on the other side, a good 180-odd million miles away. So a photograph of the sky in summer and another in winter are like your two eyes, very far apart. A nearby star will seem to shift a tiny amount against the far more distant stars behind it. Measure that shift, and geometry hands you the distance. This is called parallax, and for a long time, it was the only honest ruler we had. It is a beautiful method. It is also frustratingly short. The shifts are unbelievably small. The first person to ever succeed at it was a German astronomer named Friedrich Bessel in 1838, working on a faint star called 61 Cygni. The shift he had to measure was smaller than the width of a coin seen from several miles away. He pulled it off, and he found the star to be about 10 light-years away, which was the first time anyone had ever measured the real distance to a star. It was a genuine landmark. People had been staring at the stars for thousands of years, and Bessel was the first to reach out and put a number on how far even one of them was. But parallax fades fast. Push out past a few hundred light-years, and the shift becomes too small to catch. And the universe, it turns out, is almost entirely made of things much further away than that. So parallax gets you across the room, and the room is a tiny corner of the house. To go further, you need something cleverer. You need what astronomers call a standard candle. The idea behind a standard candle is simple, and you already understand it from ordinary life. Picture a single candle flame. Up close, it is bright. Far away, it is dim. If you know how bright the flame truly is, on its own, then by seeing how dim it looks from where you stand, you can work out how far away it must be. A car's headlights coming down a road at night, you can roughly judge the distance because you know how bright headlights are supposed to be. The trouble with stars is that they are not all the same. Some are faint little embers, some are ferocious giants. A dim-looking star might be a weak one nearby, or a brilliant one very far away, and from a single point of light you cannot tell which. So for a long time, there was no way to know the true brightness of any star, and without that, the candle trick was useless. The person who cracked this open was a woman named Henrietta Leavitt, and her story is one of the ones worth staying awake for, if you can. She worked at the Harvard College Observatory in the early 1900s as one of a group of women hired to examine photographs of the night sky. They were called computers because computing was a job done by people then, not machines. They were paid very little, around 30 cents an hour, and they were not, as a rule, allowed to operate the telescopes themselves. They studied the glass plates the men brought back. Leavitt was given the tedious task of cataloging variable stars, stars that brighten and dim over time, in two faint smudges of the southern sky called the Magellanic Clouds. She found thousands of them, and in the middle of all that patient, underpaid, repetitive work, she noticed something that nobody had seen, because nobody else had looked at so many at once. A particular kind of variable star, now called a Cepheid, pulses in brightness on a regular cycle, swelling and shrinking over days or weeks. And Leavitt saw that the ones that took longer to pulse were always, reliably, the brighter ones. The rhythm of the star told you its true brightness. A slow, lazy pulse meant a genuinely luminous star. A quick flicker meant a fainter one. Sit with what that means for a moment, because it is the key that unlocks the whole sky. If you find a Cepheid anywhere, in any far-off cloud of stars, all you have to do is time its pulse. The pulse tells you how bright it truly is. Then you compare that to how bright it looks, and the difference gives you the distance. Leavitt had turned a certain kind of star into a measuring stick you could carry out into the depths of space. She had found the standard candle astronomers had been dreaming of. She published this in 1912 in a short paper under her supervisor's name, with a quiet note that Miss Leavitt had done the work. She never got to develop it much further. She was moved on to other tasks. Her health was poor, and she died of cancer in 1921, at 53. A few years later, a mathematician in Sweden began drawing up papers to nominate her for the Nobel Prize, not realizing she had already been dead for years. The prize is not given after death, so it never happened. but nearly every measurement of the size of the universe that came afterward stood on the yardstick she built. When you hear, later tonight, how far away the galaxies are, remember that the first rung of that ladder was carved by a woman who was not allowed to touch the telescope. So now we have a real ruler that reaches far out into space. And the very first thing it did, when someone finally pointed it at the right target, was to make the universe unimaginably bigger than anyone had dared to think. Which brings us to an argument. A famous and famously unresolved argument about how big everything actually is. The argument came to a head on a spring evening in 1920 in a hall at the Smithsonian in Washington. Two respected astronomers stood up in front of their peers to debate a single question. And it is one of those questions that sounds almost quaint now, until you realize how much rode on it. The question was this: is the Milky Way the entire universe? Or is it just one island among countless others? You have to remember where people stood at the time. Through a telescope, the sky is full of faint, fuzzy patches called nebulae. Some are clearly clouds of gas inside our own galaxy, but some have a lovely spiral shape, like water going down a drain, and nobody knew what those were. One side said they were relatively small and nearby, just another kind of object inside the Milky Way, which was itself the whole of creation. The other side said no. Those spirals are entire separate galaxies, island universes, unthinkably far away, each one packed with billions of stars of its own. On one side stood Harlow Shapley, who argued for the single vast Milky Way holding everything. On the other stood Heber Curtis, who argued for the islands. Both men were careful. Both had good evidence. And in the way these things usually go, both turned out to be partly right and partly wrong. Shapley was correct that the Milky Way was much bigger than most had thought. Curtis was correct about the spirals being separate galaxies. But on the night itself, nothing was settled. The audience went home, and the question hung in the air, unresolved, waiting for someone to simply measure the answer. That someone was Edwin Hubble. And the tool that let him do it was the yardstick Henrietta Leavitt had left behind. Hubble worked at the Mount Wilson Observatory in California, which at that time had the largest telescope in the world, a giant with a mirror 100 inches across, called the Hooker. On a cold night in October 1923, he pointed it at the great spiral in the constellation Andromeda, the one you can still see faintly with your own eyes on a dark night, a soft smudge of light. He took a long exposure on a glass photographic plate, hunting for stars that flared up suddenly, the kind called novae. He found what he thought was one and marked it on the plate. Then, comparing it with earlier plates, he realized it was not a nova at all. It was a Cepheid, one of Leavitt's pulsing stars, sitting right there in Andromeda. There is a photograph of that plate, and on it you can see where Hubble crossed out his first note and wrote, in ink, a single word with an exclamation mark. VAR, short for variable. It is a very small mark on a piece of glass, and it is one of the most important things anyone has ever written down, because he could time that star's pulse, and Leavitt's law turned the pulse into a true brightness, and the true brightness, next to how faint it actually looked, gave him the distance. The number was staggering. By his measurement, Andromeda was far, far outside the Milky Way, hundreds of thousands of light years away, and by our modern figures, around 2.5 million. There was no way it could be a small cloud inside our own galaxy. It was a galaxy in its own right, a whole separate city of stars, so distant that its light had been traveling toward that photographic plate since before there were modern humans to look up at it, And here is the quiet weight of that moment. In a single measurement, the universe went from being one galaxy to being a universe of galaxies. Everything that people had ever seen, every star anyone had ever named, was now just one island. And out beyond it, in every direction, were countless other islands, most of them too far to have ever been noticed. The cosmos did not get a little bigger that night. It became almost unrecognizably larger, and it has kept getting larger in our understanding ever since. Take a slow breath with that. Just a moment ago, the Milky Way was everything. Now it is a single lit house on a street that runs on further than anyone can see. That is the feeling this whole story keeps returning to. Every time we build a better ruler, the room turns out to be a house, and the house turns out to be a city, and the city turns out to have no edge we can find. But there was something hiding inside Hubble's galaxies that was stranger than their distance. Because a quiet man in Arizona had already been studying these same spirals for years, not to measure how far away they were, but to measure how they were moving. And what he found was that they were not sitting still. Almost all of them were running away. Let's go back a few years, and a few states over, to a small observatory on a hill in Flagstaff, Arizona, and to one of the most overlooked figures in this entire story. His name was Slipher, and he worked at the Lowell Observatory. Starting around 1912, he took on a painstaking job. He wanted to measure the motion of the spiral nebulae, back when nobody yet knew what they were. To do it, he used a technique that sounds like magic, but is really just careful attention to color. When you spread a star's light out into a rainbow, a spectrum, you find it is crossed by fine dark lines, like a barcode. Those lines come from particular elements, and they always sit at particular colors. Hydrogen makes its lines in the same places every time, no matter where in the universe the hydrogen is. They are fixed landmarks in the light. Now here is the useful part. If the thing giving off the light is moving toward you, all those lines get shifted, as a group, toward the blue end of the spectrum. If it is moving away from you, they shift toward the red end. It is the same effect you hear when an ambulance passes and its siren drops in pitch as it goes by. The sound waves get stretched as the source moves away, and the pitch falls. Light does the same. Move away, and the light stretches, its line sliding toward red. This is a redshift. Move closer, and the light bunches up, sliding toward blue. A blue shift. The size of the shift even tells you the speed. So Slipher sat at his telescope, night after night, collecting the faint smeared light of these spirals, which was slow and difficult work with the equipment of the time. And when he read the barcodes, he found something he did not expect. The lines were shifted toward red. Not all of them. A few, including Andromeda itself, were shifted blue, coming toward us. But the great majority were red-shifted, and strongly. The spirals, whatever they were mostly rushing away from us, and some of them were doing it at speeds no one had ever measured before, hundreds of miles every second. Slipher did not know he was looking at other galaxies. He did not know he was watching the universe expand. Nobody had the framework yet to make sense of it. He simply reported, carefully and honestly, that the spiral nebulae were fleeing. He had the single most important clue in modern cosmology sitting in his notebooks years early, and it would take other people, using his numbers, to see what it meant, which is exactly what happened next. By the late 1920s, two halves of a puzzle were sitting in plain sight, held by different people who had not quite put them together. Slipher had the speeds. Most of the spirals were racing away. Hubble had the distances, thanks to Leavitt's Cepheids. What nobody had yet done was lay the two side by side and ask whether the speed of a galaxy had anything to do with how far away it was. Hubble did that, with a great deal of help. Much of the hard observing was done by a man named Milton Humason, and his path to that telescope is worth pausing on. Humason had almost no formal schooling. He had started at Mount Wilson as a mule driver, hauling equipment up the mountain, and then worked as a janitor at the observatory. He was patient, careful, and remarkably good with the instruments, and he worked his way up to become one of the finest observers of his generation. It was Humason, sitting through long, freezing nights, who captured the faint spectra of galaxy after galaxy and measured how fast each was fleeing. When Hubble plotted it out in 1929, the pattern was almost embarrassingly simple. The farther away a galaxy was, the faster it was moving away from us. Twice as far, twice as fast. 10 times as far, 10 times as fast. A straight line. It is one thing to hear that the galaxies are receding. It is another to learn that they obey such a plain and orderly rule about it. That straight line is now called Hubble's law, though as you might already suspect, that name is not quite fair either. Because 2 years earlier, in 1927, a Belgian priest named Georges Lemaitre had already worked it out. Lemaitre was both a Catholic clergyman and a serious physicist, an unusual pairing, and he had taken Einstein's equations of gravity and found that they did not describe a static, sitting still universe at all. They described a universe that had to be either growing or shrinking. And he went further. He took the same scattered velocity measurements that were then available, and Slipher's redshifts among them, and he estimated the actual rate at which the universe was expanding. He got there first. He published it first. The trouble was where he published it. His paper appeared in an obscure Belgian journal, in French, and almost nobody read it. When it was finally translated into English a few years later, the specific paragraph where he had estimated the expansion rate was, for a long time, missing from the translation. For decades, people assumed it had been quietly cut to protect Hubble's priority. More recent digging suggests the likelier answer is gentler, that Lemaitre himself trimmed it when preparing the English version, perhaps thinking the newer, better data made his rough early estimate not worth repeating. He was a modest man, and he seems to have simply let it go. Either way, the effect was the same. The law took Hubble's name, and the priest who saw it first slipped toward the edge of the story. In recent years, astronomers have started calling it the Hubble-Lemaitre law, a small, late correction to the record. And there was one more person even earlier, a Russian mathematician named Alexander Friedmann, who had found these same expanding and contracting solutions hiding in Einstein's equations back in 1922, working purely with the mathematics, with no thought of measuring the sky. He died young, in 1925, before any of it could be confirmed. So the discovery that the universe is expanding does not really belong to one person. It belongs to a quiet chain of them. A woman cataloging plates, a former mule driver at a telescope, a mathematician, a priest, and finally the man whose name got attached to the whole thing. So the fact itself was now clear. The universe is expanding. The galaxies are, on the whole, getting farther apart, and that single sentence, simple as it sounds, opens a door into some of the most genuinely confusing questions anyone can ask. Because the moment you say the universe is expanding, a very natural question forms, and it is the question almost everyone asks first. If the universe is expanding, then what is it expanding into? It is such a reasonable thing to want to know. When a balloon expands, it pushes out into the room around it. When a city expands, it spreads into the countryside at its edges. Expansion, in everything we know from daily life, means growing outward into some surrounding space that was already there. So surely the universe must be swelling into something, some vast emptiness beyond its edge, waiting to be filled. Right. And this is where you have to gently let go of the everyday picture, because it quietly leads you wrong. The honest answer, as strange as it feels, is that the universe is not expanding into anything. There is no edge pushing outward into a void. The expansion is not the galaxies flying apart through space, like debris from an explosion spreading into an empty room. It is space itself, the very distance between things, quietly growing everywhere at once. There is an old picture that helps, and it is worth holding in your mind as you lie there. Imagine a balloon, only slightly inflated, and imagine you have drawn little dots all over its surface with a marker. The dots are galaxies. Now start to blow the balloon up. As the rubber stretches, every dot moves away from every other dot. Pick any dot and sit on it, and you will see all the other dots receding from you, and the ones farthest away across the balloon receding fastest. Exactly Hubble's law. But now ask the key question. Which dot is the center? Which dot is the one everything is expanding away from? There isn't one. On the surface of the balloon, no dot is special. No dot is the middle. Every dot sees itself as the still point with everything fleeing from it, and every dot is equally right and equally wrong. The center of the expansion is not on the surface at all, and the surface of the balloon is the whole of the universe in this picture. The stretching rubber is space. The galaxies are not moving across the rubber. They are sitting still on it, while the rubber itself grows between them. Now, the balloon has an inside and an outside, and that is where the picture can mislead you, so set that part aside. The rubber surface is meant to be everything. There is no inside, no outside, no room the balloon sits in, just the surface and the stretching. When people ask what the universe is expanding into, they are imagining the room around the balloon. But that room is not part of the model, and as far as anyone can tell, it is not part of reality either. The growing does not need an outside to grow into. The distances inside simply get larger, and that is the whole of it. So there is no center of the universe. Let that be a strange comfort as you settle in. You are not off in some far corner of things, and you are not at the middle either. Wherever you are is a perfectly good place to call the center, because everywhere can, and nowhere truly is. Every galaxy, on every world, sees the same thing you see. A sky full of neighbors, drifting slowly away in every direction, with no special point anywhere. It is one of the few genuinely democratic facts about the cosmos. Once you have sat with the idea that space itself is growing, another confusing thing follows almost immediately, and it is one that trips up nearly everyone the first time, because it sounds like it breaks a rule you have heard your whole life. You have probably been told that nothing can travel faster than light. It is one of the firmest rules in physics, and yet the distant galaxies are receding from us faster than light, right now, and it does not break the rule at all. Both of those things are true at once, and the way they fit together is quietly wonderful. Remember Hubble's simple line: the farther away a galaxy is, the faster it recedes. Twice as far, twice as fast. Now just follow that rule outward and don't stop. Keep going to galaxies that are very, very far away. Their recession speed keeps climbing with distance, and at some point, out there at a certain vast distance, the speed of recession reaches the speed of light, and past that distance, it exceeds it. Galaxies beyond that line are being carried away from us faster than light travels. The reason this does not violate anything is the same reason from before. Those galaxies are not moving through space at that speed. If you were standing next to one of them, you would find it sitting quietly among its own neighbors, drifting only gently as we drift among ours. Nobody, anywhere, is racing through their local space faster than light. What is happening is that the enormous amount of space between us and them is all stretching at once, and when you add up all that stretching across such a huge distance, the total separation grows faster than light can cover it. The cosmic speed limit is a rule about moving through space. It says nothing about how fast space itself is allowed to grow. And space, it turns out, does not care about the limit at all. This has a consequence that is worth holding gently, because it is a little melancholy and a little beautiful. It means there is a horizon to what we can ever see. There are galaxies out there whose light is trying to reach us, setting out across the space between. But the space between is growing faster than the light can cross it. That light is, in a sense, swimming against a river that flows faster than it can swim. It will never arrive. Those galaxies are real, and they are out there, full of stars and perhaps worlds, and we will never receive another photon from them. They have slipped beyond the edge of the visible, carried off by the expansion. So the universe we can observe has a boundary, not a wall, not an edge to space itself, but a limit on how far the light has been able to reach us given the whole history of the expansion. We call it the observable universe, and everything we will ever know sits inside it. Beyond it lies more universe, very probably far more, but it is over the horizon, and the horizon is quietly moving. As the expansion carries on, more and more of what we can currently see will eventually cross that line and wink out of reach, red-shifted away into silence. Not in your lifetime, or your children's, or for an unimaginably long time yet. But it is the direction things are heading. And it is worth pausing here before we go further out, because this is a good moment to notice something about the whole subject. The universe keeps rewarding careful measurement with answers that feel almost too strange to be allowed. The night sky should be on fire, and it isn't. The Milky Way should be everything, and it's one of billions. Nothing can outrun light, and yet whole galaxies do. Each time, the strangeness is not a mistake. It is the universe being honest with us, once we finally build a good enough instrument to hear it. So let's keep going. Back to the person whose equations started all of this, and to a mistake he spent years regretting, before it turned out not to be a mistake at all. The person is Albert Einstein, and the year the trouble began is 1917, a little before most of the discoveries we have been talking about. Einstein had recently finished his masterpiece, the general theory of relativity, which is our deepest description of gravity. It treats gravity not as a force pulling objects together, but as the bending of space and time by everything that has mass. It is a strange and gorgeous idea, and it has passed every test thrown at it for over a century. But when Einstein turned his new equations toward the universe as a whole, they told him something he did not want to hear. They told him the universe could not be sitting still. Gravity, in his own theory, pulls everything toward everything else. A universe full of matter, left alone, should be falling inward under its own gravity, slowly contracting. Or, if it started out moving apart, expanding. What it could not do was hang there, static and eternal, which is exactly what everyone at the time, Einstein included, believed it did. The stars seemed fixed. The heavens seemed changeless. A calm, eternal universe was simply common sense. So Einstein did something he would come to regret. To force his equations to describe the still, unchanging universe he expected, he added a new term to them by hand. A kind of gentle pressure built into space itself, pushing outward, precisely balanced to cancel the inward pull of gravity and hold everything in place. He called it the cosmological constant. It was not something he had discovered in the mathematics. It was something he inserted to make the answer come out the way he thought it should. And for a few years, it held his imaginary static universe in a delicate, motionless balance. Then the observations arrived. Slipher's fleeing spirals, Hubble's straight line, Lemaitre's expanding solutions. The universe, it turned out, was not static at all. It was doing exactly what Einstein's untouched equations had wanted to do in the first place. It was expanding. The balance he had so carefully built was not only unnecessary, it was propping up a picture of the cosmos that was simply wrong. Had he trusted his original equations, he could have predicted the expansion of the universe years before anyone measured it. It would have been one of the greatest predictions in the history of science. There is a famous story that Einstein later called the cosmological constant, the biggest blunder of his life. That line gets repeated everywhere. It is worth saying that the quote comes to us secondhand through the physicist George Gamow, and there is real doubt about whether Einstein ever put it quite that way. It may be a little too neat to be true, but whatever words he used, he clearly regretted the fudge, and he dropped the constant, and for a long time, so did nearly everyone else. It was filed away as a great man's embarrassing mistake, a term he never should have written down, and it stayed filed away, quietly, for most of a century, until the day the universe brought it back and made it the most mysterious thing in all of physics. But we will get to that. Let's stay in the past a little longer. Once you accept that the universe is expanding, that the galaxies are drifting apart, a simple and rather childlike thought arrives. If everything is moving apart now, then long ago it must all have been closer together. And if you run the film backward far enough, all of it, every galaxy, every star, every atom, must once have been packed into something incredibly small and dense and hot. There must have been a beginning. Lemaitre, the priest, had thought this through carefully. If the universe is growing, then rewind, and it shrinks to a point. He imagined the whole of the cosmos beginning as a single dense seed, which he called the primeval atom, a kind of cosmic egg that broke apart and became everything. It was a bold, almost poetic idea, and it was the seed of what we now call the Big Bang, though the name itself came later, and it came as an insult, because not everyone liked this picture at all. A brilliant and stubborn British astronomer named Fred Hoyle found the idea of a sudden beginning distasteful. It felt too much like a moment of creation, too abrupt, too close to something outside of science. Hoyle preferred a different picture, one he developed with two colleagues, Hermann Bondi and Thomas Gold. They proposed what became known as the steady-state universe. In their version, the universe was expanding, yes, but it had no beginning and no end. As the galaxies drifted apart and new space opened up between them, tiny amounts of new matter were continuously, quietly created in the gaps, just enough to keep the overall density of the universe the same forever. The cosmos would always look roughly as it does now, eternal, unchanging on the large scale, comfortingly free of any fiery start. It was a serious idea, held by serious people, and for a while, it was a real contest. two pictures of the universe, side by side, one with a beginning, one without. And it was Hoyle himself who, during a radio talk in 1949, reaching for a way to describe the rival theory to a general audience, called it this idea of a Big Bang. He meant it dismissively. He was pointing at what he saw as the silliness of the whole thing, everything erupting from nothing in one go. The name was too vivid to die. It stuck to the theory he was arguing against, and today almost everyone knows the phrase, and almost no one remembers it, began as a bit of a sneer. Now, here is what made this argument something more than two camps trading opinions. The Big Bang idea made a prediction. If the universe really did begin in an incredibly hot, dense state, then in those first moments it would have been filled with fierce radiation, a universe glowing white-hot everywhere at once. And as the universe expanded and cooled over billions of years, that radiation would not simply vanish. It would still be here, stretched out by all that expansion, cooled down to a faint whisper. Two physicists working with George Gamow, named Ralph Alpher and Robert Herman, actually calculated this back around 1948. They predicted that the whole sky should be gently glowing, not with visible light, but with a cold radio hiss, the faded afterglow of the beginning, sitting at just a few degrees above the coldest possible temperature. Then, for the most part, their prediction was set aside and quietly forgotten. Nobody went looking. The tools to find such a faint signal barely existed, and the idea drifted out of view for the better part of 2 decades. The steady-state universe, by contrast, predicted no such glow. In an eternal universe with no hot beginning, there would be no leftover fire. So the two theories, without anyone quite framing it as a duel, had been handed away to settle their difference. If that faint, cold hiss was really out there, filling all of space, the universe had a beginning. If space was silent, perhaps it did not. The answer was sitting in the sky, waiting, and it would be found completely by accident, by two men who were not looking for it, and who spent almost a year convinced they simply had a dirty antenna. Let's go to New Jersey, to a quiet hill at Holmdel, and to one of the loveliest accidents in the history of science. In the early 1960s, at the Bell Telephone Laboratories, there stood a large and unusual antenna, shaped a bit like an enormous horn tipped up toward the sky. It had been built for early work with communication satellites, bouncing signals off balloons in orbit. Two young radio astronomers, Arno Penzias and Robert Wilson, got permission to use it for pure research, to study the faint radio emissions from our own galaxy. To do that well, they needed to understand every possible source of noise in their equipment, so they could subtract it away and be left with only the real signal from space. And they had a problem. No matter where they pointed the horn, no matter the time of day or the season, there was a faint, steady hiss in the data that they could not get rid of. A low background of radio noise coming from every direction in the sky equally. It did not rise or set with any star. It did not come from any city, or from the sun, or from the galaxy. It was just there, everywhere, all the time, a soft, constant static that would not go away. They were meticulous and a little exasperated, and they set about hunting down the source, certain it had to be a fault in their own machine. They checked every connection. They cooled their instruments to reduce noise. And along the way they discovered that a pair of pigeons had taken up residence inside the horn and coated the interior with droppings, which Penzias delicately referred to in writing as a white dielectric material. They evicted the pigeons. They climbed inside and scrubbed the antenna clean. And still, the hiss remained faint, uniform, coming from all of space at once, refusing to be explained. What Penzias and Wilson did not know was that only about 40 miles away, at Princeton, a group of physicists led by Robert Dicke had independently worked their way back to the old prediction. Dicke and his colleagues, among them a young theorist named Jim Peebles, had reasoned that if the universe began hot, there should be a faint afterglow filling the sky, and they had begun building an antenna of their own to go and look for it. They were, without knowing it, in a quiet race, and they were about to lose it to two men who had already found the thing and thought it was a nuisance. The connection was made through a phone call and a shared acquaintance. Penzias, mentioning his stubborn noise problem to another astronomer, was pointed toward the Princeton group. He called Dicke. As Dicke listened and asked a few careful questions, he understood at once what the men at Bell Labs had stumbled into. He hung up the phone, turned to his team, and said, more or less, "Well, boys, we've been scooped." The signal they had been preparing to hunt for had already been sitting in someone else's data for months, dismissed as a fault. The two groups agreed to publish together, side by side, in 1965. Penzias and Wilson reported their mysterious excess noise, plainly and modestly, without much interpretation. The Princeton group, in the companion paper, explained what it meant, and what it meant was enormous. That faint, uniform hiss, coming equally from every direction, cooled to just under 3 degrees above absolute zero, was the light of the early universe. It was the afterglow of the Big Bang, exactly as predicted, stretched and cooled by billions of years of expansion into a whisper of microwaves. For their accidental discovery, Penzias and Wilson would later receive the Nobel Prize. Take a moment with what this light actually is, because it is one of the most quietly astonishing facts in all of science, and it is a lovely thing to fall asleep on. For the first few 100,000 years after the beginning, the universe was so hot and dense that it was not transparent. Light could not travel freely. It was constantly scattered, bounced around, trapped in a glowing fog of particles, the way light is trapped inside the body of the sun. The whole universe was an opaque, blinding haze. Then, around 380,000 years in, the universe expanded and cooled just enough for the particles to settle into calm, neutral atoms, and all at once the fog cleared. Space became transparent, and the light that had been trapped was suddenly free to fly in every direction, unobstructed. That light has been flying ever since, for over 13 billion years, and a tiny part of it, after all that time, after being stretched by all that expansion, is arriving right now from every point in the sky and landing on antennas and detectors and, in a small way, on you. It is the oldest light there is. It is a baby picture of the entire universe, taken at the moment it first became clear enough to photograph. When you look up at the dark between the stars, that darkness is not empty. It is filled, evenly, with the faded glow of the beginning of everything. There is even a homely version of this you may remember. On the old televisions, the kind with an antenna, if you turned to a channel with no station, you got a screen full of dancing static and a hiss of noise. A small fraction of that static, a few % of it, was this very radiation, the afterglow of the Big Bang, being picked up by your living room television. People sat and watched the beginning of the universe as background noise and complained that there was nothing on. And with that discovery, the long argument was mostly over. The steady state universe, elegant as it was, had predicted no such glow. And here it was, filling the sky, matching the hot beginning almost perfectly Most astronomers came around. The universe had a beginning after all. Hoyle, to his credit and his stubbornness, kept looking for other explanations for the rest of his life, and he was a great enough scientist that his doubts sharpened everyone else's answers. But the weight of the evidence had shifted, and it has only grown heavier since. The faint hiss from Holmdel is now one of the cornerstones of everything we believe about where the universe came from. So by the middle of the 20th century, the picture seemed, if not simple, at least settled in its broad shape. The universe began hot and dense nearly 14 billion years ago. It has been expanding and cooling ever since. The galaxies are drifting apart, carried on the growing of space. And gravity, the great inward pull, was gently slowing that expansion down, like a ball thrown upward that rises more and more slowly as the Earth tugs it back. The only real question left, people thought, was how the story ends. Would gravity eventually win, halt the expansion, and pull everything back together into a great collapse? Or would the universe just barely escape and coast outward forever, slowing but never quite stopping? It seemed like the whole future of the cosmos came down to that one measurement. How fast is the expansion slowing down? And so, in the 1990s, two competing teams of astronomers set out to measure exactly that. They expected to argue over how much the universe was decelerating. Instead, they found something that nobody had ordered, something that brought Einstein's abandoned mistake roaring back to life and left cosmologists genuinely stunned. They found that the expansion is not slowing down at all. To understand what they found, you need to know about a very particular kind of exploding star, because it became the next rung on the ladder, reaching even further than Leavitt's pulsing Cepheids could. It is called a Type 1, a supernova, and the useful thing about it is that these explosions are remarkably alike. They happen when a certain kind of dead star, a dense cinder called a white dwarf, pulls in a little too much matter from a companion and tips past a critical limit. At that point, it detonates, and because the limit is nearly the same every time, the explosion reaches nearly the same true brightness every time. They are, in effect, standard candles you can see across billions of light years. A little cosmic flashbulb that always fires at the same strength. So, if you find one of these supernovae in a distant galaxy, and you know how bright it truly is, then measuring how bright it looks tells you how far away it is, and measuring its redshift tells you how much the universe has expanded since the light left. Put many of them together, near and far, and you can chart the whole history of the expansion. You can see whether it was faster in the past and is slowing now, which is what everyone expected, or something else. Two teams took up this hunt in the 1990s, and they were rivals. One, the High Z Supernova Search Team, included Brian Schmidt and a young researcher named Adam Rees. The other, the Supernova Cosmology Project, was led by Saul Perlmutter. Both were chasing the same faint, fleeting explosions in far-off galaxies, racing to catch them before they faded, working through mountains of data. And both expected the same result. They were there to measure how much gravity had slowed the expansion down. The only debate they anticipated was over the exact amount of the slowing. What they found, independently, around 1998, was the opposite of what they went looking for. The distant supernovae were too faint, fainter than they should have been, even in a universe that was merely coasting. And fainter meant farther. Those explosions were farther away than they had any right to be. The only way to make sense of it was almost too strange to say out loud. The expansion of the universe was not slowing down under gravity's pull. It had, billions of years ago, begun to speed up. Something was pushing the galaxies apart faster and faster, overwhelming gravity across the vast, empty distances. Both teams checked and rechecked and tried to find the mistake, because a result like this invites every doubt. Maybe the distant supernova were dimmer for some other reason. Maybe dust was in the way. Maybe those ancient explosions were simply different from nearby ones. They worked through the possibilities, and the acceleration held. And when the two rival groups, using different supernovae and different methods, arrived at the same impossible answer, the field had to take it seriously. The universe is not just expanding. Its expansion is accelerating. For confirming this, Perlmutter, Schmidt, and Rees would share the Nobel Prize years later. And here is the part that should make you smile as you lie there in the dark. To explain this outward push, this gentle pressure built into empty space that drives the galaxies apart, physicists reached back into history and pulled out the very thing Einstein had thrown away, the cosmological constant, the fudge factor he had invented to hold the universe still, then abandoned in embarrassment when he learned it was expanding. It came back. Only now it was not holding the universe still. It was doing something he never imagined, pushing it apart at an ever-growing rate. The biggest blunder of his life, if he ever really called it that, turned out to describe something real. He had written down the right idea for entirely the wrong reason, and then discarded it, and it waited 80 years to be proven right. We gave this mysterious outward push a name. We call it dark energy. And you should know that the name is mostly a label for our ignorance. It is a placeholder, a way of pointing at something we can measure the effects of, but genuinely do not understand. Dark energy appears to be a property of empty space itself. Every cubic centimeter of vacuum, every bit of nothing, seems to carry a tiny amount of this outward pressure. There is not much of it in any small volume. But space is overwhelmingly made of emptiness, and there is so much of it, and more of it opening up all the time as the universe grows, that in total, it dominates everything. How much does it dominate? This is the fact that reframes your whole sense of the cosmos. When astronomers add it all up, everything we have talked about tonight, all the stars, all the galaxies, all the glowing gas, every atom of ordinary matter, makes up only about 5% of the universe. Another roughly quarter is dark matter, a different mystery, an unseen substance that holds galaxies together with its gravity. And all the rest, around 68%, more than 2/3 of everything that exists, is this dark energy. This thing we cannot see, cannot catch, and cannot explain. The universe is mostly made of a mystery, with a second mystery for company, and the tiny leftover fraction is the only part we have ever actually touched. Sit with that, gently, without any need to solve it. Everything you have ever seen, every star that has ever been named, the entire glowing catalog of the visible universe, is a thin froth on the surface of something vast and dark that we do not comprehend. We spent centuries learning to measure the cosmos, and the better we measured, the clearer it became that the part we can see is the small part. It is a humbling place to arrive, and it is, honestly, a strangely peaceful one. There is a great deal out there that does not need us to understand it in order to go on doing what it does. There is one more piece of the expansion worth sitting with before we turn for home, and it is the strangest of all, because it did not happen far away or long into the story. It happened at the very beginning, in the first sliver of the first second, and it involves the universe expanding faster than it ever has since, or ever will again. To see why anyone would propose such a wild thing, you have to start with two quiet problems that the simple Big Bang picture could not explain. Two things that should not have turned out the way they did. The first problem is about how astonishingly even the universe is. Remember that afterglow, the cosmic microwave background, the faint light from the early universe coming at us from every direction. When astronomers measured its temperature, they found it was almost exactly the same everywhere, to a remarkable degree, no matter which patch of sky they looked at. One side of the sky, the other side of the sky, the same temperature to within a tiny fraction of a degree. And that is strange, when you think about it, because those opposite patches of sky are so far apart that, in the ordinary history of the universe, they could never have touched. Light itself would not have had time to cross between them. They have never been in contact, never traded any heat, never had any way to settle on a common temperature, and yet they match almost perfectly, as if they had. It is a bit like meeting two people from opposite ends of the earth who have never spoken, and finding they are humming the same tune, at the same pitch. How did regions that could never communicate come out so identical? The second problem is about the shape of space itself. The universe, as far as we can measure, is flat. Not flat like a sheet of paper, but flat in a deeper geometric sense, meaning that on the largest scales, parallel lines stay parallel, and the ordinary rules of geometry hold. Space could have been curved. In principle, it could have curved in on itself or curved outward, and there was no obvious reason it should be balanced so precisely in between. But it is balanced there, extraordinarily finely. And for it to be that flat now, it would have had to be almost unbelievably flat at the beginning, tuned to a razor's edge. A universe just slightly off would have long since curled up or flown apart. Ours sits right on the knife edge, and nobody could say why it should. So you have two things that the plain Big Bang leaves unexplained: a universe too even, and a universe too flat. In 1980, a young physicist named Alan Guth was turning these puzzles over, and he came upon an idea so bold it almost sounds like cheating, except that it solves both problems at once, which is usually a sign that an idea is worth taking seriously. His idea is called cosmic inflation. Here is the picture. Imagine that in the very first instant, a fraction of a second so small there is no ordinary word for it, the universe went through a brief and violent burst of expansion. Not the gentle, steady expansion we have talked about all night. Something far more extreme. In that flicker of time, the universe doubled in size, and doubled again and again, over and over, growing by an enormous factor almost instantly, faster than at any moment before or since. A region far smaller than a single atom was blown up, in the blink of a fraction of an eye, to something larger than a grapefruit, and the whole observable universe grew out of that. And watch how neatly it fixes both problems. Before inflation, the region that became everything we can see was so unimaginably small that all of it was in easy contact. It had plenty of time to settle into one even temperature, the way a small room settles to one warmth. Then inflation seized that tiny, already even patch and stretched it out to enormous size in an instant, carrying its evenness with it. So opposite sides of the sky match, because they were once neighbors, pressed close together before the great stretching flung them apart. They agree because they share a childhood. That is the first problem, solved. And the flatness too, Take any curved surface and stretch it enormously, and any small piece of it looks flat. Blow up a balloon to the size of a planet, and the patch right in front of your face looks perfectly flat, though the hole is still round. Inflation stretched space so violently that whatever curvature it started with was flattened almost completely, ironed smooth by the sheer scale of the expansion. So the universe looks flat because it was pulled flat in the first instant. Two deep puzzles, one idea, and inflation gave a bonus, something no one designed it to do, which is often how you know you are onto something. In that first instant, the universe was small enough to be ruled by the strange rules of the very tiny, where faint, random ripples flicker in and out of existence in even the emptiest space. Inflation took those minuscule ripples and stretched them too, up to cosmic size, freezing them into the fabric of the growing universe. And those stretched ripples became the faint patterns we later see in the afterglow, the very slightly warmer and cooler patches in that even glow. And those patches became the seeds around which matter gathered, the places where galaxies would eventually form, which means the largest structures in the universe, the great web of galaxies we drifted through earlier, may have grown from the tiniest flickers of the very small, blown up to unthinkable size in the first moment of everything. Inflation fits the observations remarkably well, and most cosmologists accept some version of it. But do not mistake that for understanding. Nobody knows exactly what drove it. There must have been some field, some property of the early universe that powered that violent stretch and then switched off, handing over to the gentle expansion we live in now. That thing has a placeholder name, and it remains almost entirely mysterious. We do not know what it was, why it started, or why it stopped. We have a lovely idea that solves several problems at once and matches the data, and we still cannot tell you what actually happened, which is by now a familiar feeling in this story. The expansion keeps handing us answers that work and that we cannot fully explain. So even the very beginning of the expansion holds a mystery we have not closed, and it is far from the only one still open. Some of the confusions in this story are ancient, buried in the first fraction of a second, but some of them are not ancient at all. Some of them are being argued over this very year, by people who are alive right now, over a number you would think we had settled long ago. Now we come to the confusion that is happening right now, tonight, while you rest. Because you might think, after all these decades of work, that at least we would know the simplest number of all, the rate of the expansion itself, how fast the universe is growing. That single number, the one Lemaitre first estimated and Hubble made famous, is called the Hubble constant, and it sets the scale for the size and the age of everything. You would expect by now that we would have it pinned down cleanly. And this is the strange part. We have measured it two different ways, both of them very carefully, and the two answers do not agree. They stubbornly, persistently refuse to agree, and nobody knows why. Here are the two ways, gently. The first is to measure the expansion here and now, in our own cosmic neighborhood, using the ladder we have been building all night. You find Cepheid stars, Leavitt's pulsing candles in nearby galaxies. You use them to calibrate the brightness of type 1, a supernovae. And then you use those supernovae to reach far out and watch how fast distant galaxies are receding. It is the direct approach, climbing the distance ladder rung by rung, and the team that does this most carefully, led by that same Adam Rees from the dark energy discovery, arrives at a value of around 73 in the units cosmologists use. The second way comes at it from the opposite end of time. Instead of measuring the expansion nearby, and now you measure the infant universe, using that faint afterglow, the cosmic microwave background. That baby picture of the cosmos is full of subtle patterns, tiny ripples in the glow, and those patterns are set by the physics of the early universe. If you understand that physics, and we believe we do, quite well, you can use the ripples to predict how fast the universe should be expanding today. When the Planck satellite mapped that ancient light in exquisite detail and the numbers were run forward, the answer came out around 67. A little slower. 73 from the nearby measurements. 67 from the early universe. Those two numbers do not sound very far apart, and if this were a casual estimate, you would shrug and call them close enough. But these are not casual estimates. They are two of the most carefully checked measurements in modern science, each with small and shrinking uncertainties, and the gap between them has not closed as the measurements have improved. It has gotten sharper. Each side has gone back over its work again and again, hunting for the hidden mistake, and the disagreement keeps surviving. This standoff has a name now. People call it the Hubble tension, and it is one of the liveliest puzzles in all of cosmology. So which is it? Is the universe expanding at the slower early rate or the faster nearby one? And how can two good measurements of the same thing come apart like this? There are really only two kinds of answer. The first, the tidy one, is that somebody has made a subtle error somewhere. Some small thing not yet understood in how one of the measurements is made, and once it is found, the two numbers will slide together, and everyone will feel a little foolish and a little relieved. That is entirely possible, and many careful people suspect it. But the second possibility is the one that makes physicists sit up at night. It is that both measurements are right, that the universe really does seem to be expanding faster now than the early universe predicts it should. And if that is true, then something is missing from our understanding. Some ingredient in the story, some new kind of physics acting between the infant cosmos and the present day that we have not yet accounted for. Perhaps dark energy is not quite the simple, constant thing we assumed. Perhaps there was some extra push in the early universe. Nobody knows. That is the honest state of it. This is not a settled subject with the answer hidden in a textbook. It is an open question, being argued over in papers and at conferences as you drift off, by people who genuinely do not yet know how it will resolve. And it is worth appreciating that this is a wonderful kind of confusion to have. It is the confusion of a field that has measured its way into a corner where its own best answers disagree, which is exactly the situation that has, again and again, cracked open something new. The night sky being dark led to the expansion. Einstein's discarded constant led to dark energy. A stubborn hiss in an antenna led to the beginning of everything. Each time, the thing that did not fit was not a failure. It was a door. The Hubble tension may turn out to be a small measuring error, or it may turn out to be a door, and the people alive right now are the ones who get to find out. There is something comforting in that, honestly. The story is not finished. It is still being written, gently, in the dark, by people who love it. Let's step back from the argument now and pull the camera all the way back, as far as it will go, to look at the size of the thing we have been talking about this whole time. Because there is one last confusing number, and it is the biggest and strangest number in this entire story, and it makes a wonderful place to begin our slow journey home. The universe is about 13.8 billion years old. That is the time since the beginning, and it is measured well from several directions that agree. Now, light travels at a fixed speed, and nothing carries information faster. So it is natural to think that the farthest we could possibly see is 13.8 billion light-years in any direction, because that is how far light could have traveled in the whole age of the universe. A sphere 13.8 billion light-years in radius, with us in the middle. That would be a reasonable guess. And it is wrong, and the reason it is wrong is the quiet thread that has run through this entire night. The most distant light we can see did set out around 13.8 billion years ago, near the very beginning. But while that light was traveling toward us, all those billions of years, the space it was crossing kept expanding. The ground beneath the light, so to speak, kept stretching. So the galaxies and gas that emitted that ancient light are not 13.8 billion light-years away now. They have been carried much, much farther out by the expansion while their light was in transit. When you do the calculation properly, accounting for all that stretching, the edge of the observable universe sits at around 46 billion light-years away in every direction. The light crossed 13.8 billion years of time, but the distance it effectively spanned by now is more than 3 times that. So the observable universe is a sphere about 93 billion light-years across, and every bit of it is centered on you, because it is centered on any observer anywhere. That is the largest thing this story has to offer, and even that, remember, is only the part we can see. The whole universe is almost certainly much larger, possibly far larger, possibly without any end at all. What lies past our horizon we cannot know, because its light has never reached us, and, thanks to the accelerating expansion, most of it never will. We live inside a bubble of visibility, a sphere of light that has had time to arrive, floating in a cosmos whose true size is simply beyond our reach. And that same acceleration, the dark energy pushing everything apart faster and faster, is slowly changing what that bubble contains. Here is the last strange thing, and it is a gentle sort of sad, and then a gentle sort of comforting. As the expansion speeds up, the distant galaxies are being carried away from us faster and faster, and one by one, over unimaginable spans of time, they will cross beyond our horizon. Their light will stretch and redden and dim until it fades from reach entirely. The sky, very slowly, is emptying. Now, do not worry for our own neighborhood. The galaxies closest to us, our own Milky Way, Andromeda, and a few dozen smaller ones, are bound together by gravity into what we call the local group, and gravity holds them firmly against the expansion. They are not being pulled apart. In fact, the Milky Way and Andromeda are drifting toward each other, and billions of years from now, they will merge into a single larger galaxy. That much will stay together. But everything beyond the local group, all the countless other galaxies, all the distant light that told us the universe was expanding in the first place, is destined to recede beyond the edge of what can be seen. Think about what that means for whoever might be around in the far, far future. Imagine astronomers on some world, 100 billion years from now, long after the other galaxies have vanished over the horizon, and the faint afterglow of the beginning has stretched away into undetectable silence. They would look out and see only their own island of stars, the merged remains of our galaxy and its neighbors, surrounded by what looks like endless, eternal, empty black. They would have no galaxies to watch receding, no redshift to measure, no cosmic hiss to stumble on. Every clue we use to piece together this story would be gone. They might well conclude, quite reasonably, that they live in a single static galaxy in an unchanging void, and they would have no way to know they were wrong. The evidence would have expanded out of their reach, which means, And this is a thought worth resting on, that we are living in a particular and rather fortunate moment. The universe is old enough that we can see and understand what it is doing, and young enough that the evidence has not yet slipped away. We can still see the galaxies fleeing. We can still catch the afterglow. We arrived late enough to have the tools, and early enough to still have the view. The window is open now. It will not stay open forever, in the deepest sense of forever, but it is open now, tonight, and we are here to look through it. There is something quietly lucky about that. And on the far end of all this lies the ultimate fate, which nobody knows for certain, so we hold it loosely. In the most likely picture, the universe simply keeps expanding and cooling forever. The stars slowly burn out, one generation after another, with no new gas left to make more. The galaxies drift apart into isolation. The lights go out, gradually, over spans of time so vast they make the current age of the universe look like a single breath. It winds down, gently, into a cold and quiet dark. Some physicists have wondered about stranger endings, where dark energy grows stronger and eventually tears even atoms apart, a dramatic finish sometimes called the Big Rip. But that is speculation at the edge of what we know, and the evidence does not favor it. The calm, slow fading is the more likely path, and it is so far away in time that it need not trouble you at all. So that is the shape of the whole thing. A universe that began hot and small, that has been expanding for nearly 14 billion years, that is picking up speed under a dark energy we cannot explain, that we can measure two ways which do not quite agree, and that is, even now, gently carrying its most distant lights out of our sight. It is confusing. It is meant to be confusing. We have only been looking at it clearly for about a century, and every good instrument we have built has made it stranger, not simpler. And now, having gone all the way out to the edge, let's begin the slow journey back inward, back down through all of it, home to this room and to you. But before we come all the way down, there is one more gentle confusion to clear away, and it is the one that matters most for how you feel lying here. So it is a good one to settle before sleep. If the whole universe is expanding, if space itself is stretching everywhere, then a worry naturally follows. Is everything stretching? Are you stretching? Is the bed slowly growing? Is the room quietly getting bigger? Are the very atoms in your body being pulled apart along with the galaxies? It would be an unsettling thought if it were true. And it is not true. And the reason it is not true is lovely. The expansion of the universe only wins where nothing else is holding things together. Out in the vast, empty gulfs between galaxy clusters, there is almost nothing. Gravity out there is faint, spread thin across enormous distances, far too weak to resist the stretching. So in those great voids, space grows, and the distant galaxies drift apart. That is where the expansion has its way. But come in closer, to anywhere that matter has gathered, and other forces take over completely, and they win easily. Think of the balloon again, with the dots drawn on it. As the balloon inflates, the dots move apart. But the dots themselves do not grow. Each little dot stays exactly the same size, because the ink is bound together, holding its shape, while only the empty rubber between the dots stretches. The galaxies are the dots, and you, and everything you have ever touched, are far, far smaller and far more tightly bound than any dot. Your body is held together by the forces between atoms, and those forces are staggeringly strong compared to the gentle pull of cosmic expansion. There is no contest. The expansion does not stand a chance against the bonds in a single molecule of you. The Earth is held together by gravity and by the strength of rock, and it holds its size. The solar system is bound to the sun, circling in its steady orbits, and it is not growing. Even the Milky Way, 100,000 light years across, is held together by its own gravity, and it is not expanding. Even our local group of galaxies is bound tightly enough to resist. You have to go beyond all of that, out past the nearest clusters, into the truly empty spaces, before expansion becomes the strongest thing around. So nothing near you is stretching. Not the bed, not the room, not your body, not the ground under the building. The rulers stay the same length, which, when you think about it, is the only reason we could ever notice the expansion in the first place. If everything grew together, every distance and every measuring stick alike, there would be no way to tell, and nothing would ever look any different. The expansion is real precisely because it does not touch the small, held-together things. It only opens up the great empty distances, far away, between the islands of light. There is a quiet comfort in that. The universe is doing something enormous and strange, carrying whole galaxies apart faster than light across distances you cannot picture. And none of it reaches into this room. Here, everything is held. Your body keeps its shape. The walls keep their places. The floor stays where it is. The vast unraveling is happening only out in the deep, where there is nothing to hold, and it leaves the small, warm gathered places, the planets, and the bodies and the beds, entirely alone. You are made of the parts of the universe that stay together. So let's come back down to them now, slowly, all the way home. Start at the edge, the very edge, 46 billion light years out, where the oldest light is still arriving. Picture that faint boundary all around, in every direction, the limit of everything we can see. Now let it begin to draw inward, past the most distant galaxies, the ones already slipping over the horizon, their light stretched almost to nothing. They are letting go of us, and we of them, and that is all right. Let them drift. Come inward, past the great cosmic web, the vast, lacy structure of the universe on the largest scale, where galaxies gather in long, glowing filaments strung around enormous dark and empty voids. It looks, from far enough away, a little like a network of threads, or the branching of something almost alive. That is the scaffolding of everything, sketched across billions of light years, and we are falling gently through it now, inward, toward one particular thread, toward one small knot of light among countless others. Come further down, to our own cluster of galaxies, and then to the local group, our little gravity-bound neighborhood, the few dozen galaxies that will stay together while the rest of the universe drifts away. There is Andromeda, the great spiral, the one Hubble measured, drifting slowly toward us across 2.5 million light years, in no hurry at all, on a journey that will take billions of years. And beside it, our own, the Milky Way. 100,000 light years of stars, wound into a slow spiral, turning so grandly that a single turn takes longer than the time since the dinosaurs. 200 billion suns or more, drifting in the dark, and you are inside it, on one small arm of it, out toward the quiet edge. Come down into that arm now, past drifting clouds of gas where new stars are being born, past old dying stars breathing their outer layers back into space, until you reach one ordinary yellow star, unremarkable among the billions, that happens to be ours, the Sun, and around it, the small familiar family of worlds, held in their steady orbits, none of them expanding, all of them circling just as they have for billions of years. Past the outer giants, past the ringed one, past the red one, until you reach the third small world from the star, the pale blue one, the only one, as far as we know, with anyone on it looking up and wondering about any of this. Come down through the thin shell of its atmosphere, the little band of air that holds all the weather and all the breathing that has ever happened, down through the clouds, to the dark side of the world, the half that is turned away from the sun right now, where it is night, where you are, down to the land, to the region, to the town, to the street, to the roof over your head, and in through it, to this room, the room you are lying in right now, at the bottom of all of it, at the end of the long fall inward from the edge of the visible universe. And here you are, a small, warm, gathered together thing, held by forces so strong the whole expanding cosmos cannot stretch you by a hair. Feel the weight of your body on the bed. Feel the places where you are held, where you are heavy, where you are still. The mattress underneath you, the covers over you, the quiet dark of the room. All of that unimaginable size we just traveled through. And here at the center of your own observable universe, because everyone is at the center of theirs, is this: a body breathing in the dark. There is nowhere further in to go. You have arrived. And now, having come all this way home, let yourself feel how the whole enormous story is written into the body lying here. Because you are not separate from any of it. You are made of it, quite literally, and this is the part that turns the cosmos from something out there into something you can hold. Every atom in you has a history that runs all the way back to the beginning we talked about. The hydrogen in the water of your body, in every cell, is very nearly as old as the universe itself. It formed in the first few minutes after the beginning, when the whole cosmos was hot enough to be a furnace, and it has been drifting through space and gathering into clouds and stars and worlds ever since. The hydrogen in you tonight is almost 14 billion years old. It was here before the sun. It will be here long after. And the heavier things, the atoms that make you more than water. The carbon in every living cell. The oxygen you are breathing in and out, slowly, right now. The nitrogen, the calcium in your bones, the iron carried in your blood. None of those existed at the beginning. There was no carbon, no oxygen, no iron in the early universe, only the lightest few elements. Everything heavier was built later, forged in the hot hearts of stars, cooked slowly over millions of years under crushing pressure, and then scattered out into space when those stars died. Some of it drifted gently off as the star breathed out its final layers. Some of it was flung across the galaxy in the violence of a supernova, and it drifted, and it gathered, and some of it became the cloud that became the sun, and the earth, and in time, you. It was Fred Hoyle, of all people, the same stubborn man who coined the phrase Big Bang as an insult and who never quite believed in it, who worked out much of how the stars build these elements. He figured out how carbon itself, the backbone of all life, could be assembled in the cores of aging stars. So the man who resisted the beginning helped show us how the middle of the story works, how the atoms of living things are manufactured in starlight. Science is generous that way. It keeps the good work even of the people who turned out to be wrong about the big picture. So the calcium holding you upright was made in a dying star. The iron that carries oxygen through you was made in a dying star. The carbon that spells out every thought you have ever had was made in a dying star. You are, in the most ordinary and literal sense, made of the ashes of things that shone long before the earth existed. The universe spent billions of years, and the lives and deaths of countless stars, assembling the specific atoms that are, tonight, lying in a bed, listening to a voice describe where they came from. That is not a metaphor. That is just the history of the material. And that faint afterglow, the light from the beginning, the hiss that Penzias and Wilson could not scrub out of their antenna, it is passing through this room right now. It is passing through you. A gentle rain of the oldest light there is, arriving from every direction, from the edge of the visible, having traveled almost the entire age of the universe to get here, and it is landing on you as softly as anything ever could, and you cannot feel it at all. The beginning of everything is in the room with you, quietly, and it asks nothing of you, and it always has been. So let that settle for a while, and let the confusion settle with it, because the confusion was never a problem to be fixed tonight. It was the whole point, and it is a gentle thing to rest in. Think of everything we still do not know, and notice how little it disturbs the quiet of this room. We do not know what dark energy actually is, this thing that makes up most of the universe and pushes it apart. We do not know why our two best measurements of the expansion refuse to agree. We do not know how large the whole universe truly is beyond the part we can see, or whether it has any edge at all, or what, if anything, came before the beginning. We do not know how the story ends, only that the ending is unimaginably far away. And none of that is a crisis. It is just the honest edge of what a young species has managed to work out so far, lying under the same sky you are lying under now. For almost all of human history, nobody knew any of this. Nobody knew the little smudges of light were other galaxies. Nobody knew the universe had a beginning, or that it was growing, or that the dark between the stars was full of ancient light. We have known these things for about 100 years. That is nothing. That is the blink of an eye against the age of the thing we are studying. We are very early in this, and being early means most of the questions are still open. And there is something restful in that, not something to worry over. You do not have to solve any of it. You do not have to remember any of it. There will be no test in the morning on the difference between a Cepheid and a supernova, or on who really discovered the expansion, whether it was Hubble or Lemaitre or Slipher or Leavitt or all of them together. It does not matter tonight. The names can go. The numbers can go. The 46 billion light years, the 67 and the 73, the 3 degrees above absolute zero. Let all of it drift out of your hands. It was never yours to carry. It was just something to listen to on the way down into sleep. Because here is the truth that makes it easy to let go. None of it needs anything from you. The universe was expanding for billions of years before anyone was here to notice, and it will go on expanding for billions more after we are all long gone. The galaxies will keep drifting apart, whether or not you are awake to picture them. The oldest light will keep raining softly through this room, whether or not you feel it. Dark energy will go on doing its slow, patient, mysterious work in the great empty spaces, asking nothing, needing no witness. It will all still be out there in the morning, exactly as it is now, carrying on without the slightest need for your attention. So you can rest. You have permission to simply let the whole vast thing continue on its own tonight. Your only task, the only thing being asked of you right now, is to lie here and be one of the small, warm, gathered together places that the expansion cannot touch. To breathe, to be held by forces older than the earth, to be, for a little while, just a quiet body in a quiet room, made of ancient hydrogen and stardust, on a small blue world, on one arm of one ordinary galaxy, drifting gently through a universe far too large and far too strange to ever fully understand. And that is enough. That is more than enough. The room is dark. The bed is holding you. The expansion is carrying on, far away in the deep, where it belongs. And you do not have to go anywhere, or know anything, or be awake for any of it. Let your breathing slow. Let the numbers fade. Let the galaxies drift. So just rest now. It will all still be here, and so will you. Good night.